So first of all, let's see the model structure on TOPE itself. Its morphisms are of course continuous functions, and we claim that the model structure is as follows. Weak equivalences are weak homotopy equivalences, fibrations are Serre fibrations, and cofibrations are retracts of relative cell complexes. We will write these as follows and call them classical. Once we prove this, we will be able to easily have these related model structures, the model structure on pointed topological spaces, the model structure on compactly generated and compactly generated pointed topological spaces, and even the model structure on some topologically enriched functors. The first thing we want to show is that classical weak equivalences, i.e. weak homotopy equivalences, satisfy 2 out of 3, but isomorphisms obviously do, in particular those of homotopy groups, so this follows immediately. Moving on to the factorization axioms, let's check that every morphism in TOPE factors as a classical cofibration, followed by an acyclic classical fibration. Recall our technical lemma that the image of a compact set into a relative cell complex is completely attained at some finite stage. Well, this shows that ITOPE, the topological generating cofibrations, which are the inclusion of the n-1 sphere into the n disk, have small domains, so F has a small domain as well. Using the small object argument, we can therefore factor F as an ITOPE relative cell complex, followed by an ITOPE injective morphism. Well, we showed that ITOPE injective morphisms are precisely acyclic Serre fibrations, so we have a factorization as a classical cofibration followed by a classical acyclic fibration, and we are done. Dually, let's show that we can factor any morphism as a classical acyclic cofibration followed by a classical fibration. Using the same technical lemma, since n disks are compact, we have that F is again a small domain, has small domains, so we can factor this as a J-tope relative cell complex, followed by a J-tope injective morphism. So J-tope was our classical topological generating cofibrations, if you recall. Well, then we showed that J-tope injective morphisms were Serre fibrations. Finally, we recall that J-tope cell complexes are I-tope relative cell complexes and weak homotopy equivalences. So we do have a classical acyclic cofibration followed by a classical fibration. Here's another factorization related result. If we have this commuting square, then we get a lift as soon as one of the two is also a classical weak equivalence. So one direction is something we already showed. Acyclic fibrations are precisely those that lift against generating cofibrations, and we showed in earlier corollary 211 that hence it lifts against all of its retracts. So if we have a classical weak equivalence on the left, well, we talked about, we just showed that we can factor it as a J-tope relative cell complex followed by a fibration, i.e. a J-tope injective morphism. Again, J-tope relative cell complexes are weak equivalences, so since the entire map is by assumption a weak equivalence, we have that the second map is an acyclic classical fibration by 2 out of 3. Hence it lifts against the overall map G, which is in particular a cofibration by what we just showed. Another way to phrase this is that G has a right lifting property against the second map, and so by the retract argument this gives G as a retract of the first morphism, i.e. a retract of a J-tope relative cell complex. Well, by definition, F, which is a Serre fibration, lifts against J-tope and hence against its retracts, and we're done. So this should make the final factorization axiom easier to prove, that we have these pairs as weak factorization systems. We already showed that they satisfied the lifting properties, but it's not clear that every map that lifts is contained in these pairs. We did already show way back that this is the case for classical fibrations, by definition almost, and for classical acyclic fibrations. So it remains to check for classical cofibrations and acyclic cofibrations, i.e. are these precisely the classes with the right lifting property against classical acyclic fibrations and classical fibrations respectively. So let F be a map with the right lifting property against classical fibrations, i.e. an I-tope injective projective morphism. It suffices to show that F is a retract of a relative cell complex, as then it would be a cofibration. So we can apply the small object argument to factor F as an isotope relative cell complex followed by an isotope injective morphism. Well, then F by assumption is in isotope injective projective, so it has the right lifting property against the second map, so by the retract argument is a retract of the first, i.e. a retract of an isotope relative cell complex. So it is a classical cofibration as desired. Finally, consider the case for acyclic cofibrations. So pick F in J-tope inj proj. Small object argument tells us that it's a retract of a J-tope cell complex using the process we did just now. But we showed in the last two lemmas that a J-tope relative or J-tope cell complex is an I-tope cell complex and a weak homotopy equivalence. A retract of a J-tope cell complex is thus a retract of an I-tope cell complex, i.e. a cofibration, and also a retract of a weak homotopy equivalence, i.e. still a weak homotopy equivalence. Hence F is an acyclic cofibration, and we're done. So all of that work gives us this classical model structure on topological spaces, or the Serre-Quillen model structure. Nice properties here include that every object is fibrant and the cofibrant objects are retracts of cell complexes. So we have the classical Whitehead theorem, which is a specialization of the Whitehead theorem in model categories from before. What's the deal with the generating part of generating cofibrations and acyclic cofibrations? Well, if you observe, because of certain properties we proved in topological homotopy theory, we got the entire model structure just from iTope and JTope. This is a feature of a model category called being cofibrantly generated. This means that we have two subsets of morphisms, I and J, that both have small domains, and such that the cofibrations of the category are precisely the retracts of I relative cell complexes, and acyclic cofibrations are precisely the retracts of J relative cell complexes. This means we can efficiently express all of our classes as just injective and projective morphisms, like cofibrations are I-injective, projective morphisms, etc. We'll prove the first, which will imply the second, and the third and fourth are analogous. So clearly I is at least a subset of I-injective projective morphisms, and then so too are its retracts. For the converse inclusion, consider a map F in I-injective projective. Well, by the small object argument, we can factor it as an I-relative cell complex, followed by an I-injective morphism. Well, then it has the right lifting property against the second morphism in the composition, and so by the retract argument is a retract of the first, i.e. an I-relative cell complex, and hence a cofibration.